talk about, so we're going to talk about, how many times can you repeat yourself till the thing starts playing? Common base, which we talked about last year a little bit. And we're going to talk a lot about it this year to be able to solve some things. And then we talk about it even more in 30-1. So, it's a new and necessary skill. Sometimes you've seen it before, but we're going to talk about it. So, when you're in a situation where the exponent is a variable, you're going to do your best to find common base. So the first thing we're going to do, I'm just going over this, you don't have to write it, it's in your notes. Is say you have 5 times 2n minus 1. What you will not do is you will not multiply those. You can't because the 2 has an exponent. So you won't go 10 to the n minus 1. That's the biggest error that happens. You can see why it happens. It like calls you to multiply those two. But you can't. So the first thing you actually have to do is you have to divide by 5 first. Both sides to move that 5 over. Which is what we did in the next one. Then we got 2 to the n minus 1 equals 128. So what our goal is, we don't know how to solve this algebraically. To solve that algebraically, if we don't do common base, you'd actually have to do exponents, exponential, which is in 30-1. So we're not going to go that route because you might have to convert to a log, which we also don't know how to do. So we're just going to stick with common base. So if this is 2 to the n minus 1, we need to find out if we can make this be 2 to some exponent. So in our calculator, we go 2 to the exponent 2, and we get 4. And we're like, nah, that's not 128. And then we do 2 to the 3, and we get 8. And we're like, still not 128. 2 to the power of. So you do 2 to the power of 2 is not 128. And we're using 2 because this side's a 2. You see that? Then we do 2 to the power of 3, nope. 2 to the power of 4, nope. 2 to the power of 5, nope. 2 to the power of 7. Everyone try and type that into your calculator. So you're going to go to this little hat symbol, 7. It's by the arrow. 2 to the power of 7 is 128. So that's why 2 to the power of 7 is written down here, because those are equal. Right? 2 to the power of 7 is 128. And why did we do 2 to the power of something? Because this one's 2 to the power of something. So now we have 2 to the power of n minus 1. That didn't change. Equals 2 to the power of 7. We agree? So say I gave you this. Say I gave you 2 to the smiley face equals 2 to the 6. What would you tell me smiley face would have to equal? 6, right? If 2 to the smiley face equals 2 to the 6, then smiley face must be 6. We agree? So if 2 to the n minus 1 is 2 to the 7, right? Then n minus 1 must equal 7 in order for that to be true. If 2 to the smiley face equals 2 to the 6, then 2 to the n minus 1 equals 2 to the 7, then n minus 1 must equal 7. And then we just have to solve it. How would we solve it? We would add 1. So we get n equals 8. So what we're going to practice is solving some common base dealios. Okay? So if we have 2 to the x equals 128, and I want to know what x equals, I need to make them be the smaller base. So my smaller base is 2, right? And 2 to the what is 128? We just did it above. 2 to the 7. So we could say 2 to the x equals 2 to the 7, and we say then that x must equal 7 in order for that to be true. Do we agree? So then we're going down here and reiterating what we did up there. 2 to the n minus 1 equals 128. So now 2 to the n minus 1, we need to get 128 into 2. So it's 2 to the 7 is 128, right? Now instead of saying, now once we have 2 to the exponent equals 2 to the exponent, then our exponents must equal. So we must get n minus 1 equals 7. And then how do we get n by itself? We added 1. So n equals 8. And we could check it. We could put 8 back in here. 8 minus 1 is 7. 2 to the 7 is 128. That's true. So we're not going to do the bottom ones yet. We're going to go up here. Oh, yeah, we're going to do the bottom one. Ignore me. We have to get the 2 to the x by itself. So what did I tell you to do? Not put this as a 10. What are you going to do?
5.
Divide the 5 over first. So we get 2 to the x equals 128. then we have to make them be the same base, because we've never had to deal with our variable in the exponent, right? Our variable's always been in the bottom, and we just like add or multiply or divide to get it. So now we need to make the 128 be 2 to the something. So 2 to the x equals 2 to the 7. So once again, x equals 7. So now we're going to try it for this 3. We have 3 to the x equals 6,561. What base do we need to change it to? 3 to the x equals 6,561. We have to make it be the smaller base. What base is that? The 3. So I need to go 3 to the 2 is 9. Nope. 3 to the 3, 27. Still off. 3 to the power of 4 is 81. Nope. So you do it. 3 to the 5, 3 to the 6. Find one that gets you 6,561. 3 to the 8. 3 to the 8? Try it out. Go 3 to the power of 8. Now some people may say, I can't do that in my head. I don't want you to. You're just going to go 3 to the 3, 3 to the 4, 3 to the 5, 3 to the 6 till you get it. It's match, right? And you said it was 8? That's what it says? 3 to the 8? So it's going to be 3 to the x equals 3 to the 8. So what must x equal once we have them both be the same base? 8. Because it was just a straight up x. Now this one I have 3 to the n minus 1 equals 3 to the 8, because 6,561 is 3 to the 8. Now instead of saying x equals 8, what's this one going to be? N minus 1 equals what? 8. Because this exponent must equal this one if the bases are the same. And then I need to get n by itself, so I add 1. So n equals 9. What do I have to do the bottom one first? Divide by 4. I'm going to get 6,561, which is the same as 3 to the 8. Now I have x minus 1 equals 8. Add 1. X equals 9. You try it with the 5s, the last column. 125 is 5 to the what? To the 3. 5 to the x equals 5 to the 3. So x must equal 3. And we're done. This one is 5 to the n minus 1 equals 5 to the 3. N minus 1 equals 3. Add 1. And n equals 4. And what's the first thing I have to do in this last box? 5 by 3. Not make this a 15. So I get 5 to the x minus 1 equals 125. 5 to the x minus 1 equals 5 to the 3. X minus 1 equals 3. Add 1. X equals 4. And then we're going to flip over. So a geometric sequence is one where you multiply to get to the next one. So instead of it being common difference, which was adding something to get to the next one, I said it's going to be a multiply. So it's called the common ratio. It's an R. It's called, instead of a D, the common ratio. Now, how did we find the common difference? What did we always do to find D if we were given a sequence? Yeah, so term 2 minus term 1, or term 3 minus term 2, or term 100 minus term 99, right? It was always take the term after, subtract the term before. For common ratio, we're actually going to divide the terms. So for ratio, we're going to do term 2 divided by term 1 instead of subtracting. Because division is the opposite of multiplication, and that's what a ratio is doing, it's multiplying. That's why we subtracted when we found difference, because it's the opposite of adding. So in this case, for this one up here, 3, 6, 12, 24, 48, we're going to go 6 divided by 3, which is 2. I could even try 48 divided by 24. Still 2, right? So we're multiplying by 2 to get to the next one instead of adding. Difference between geometric and arithmetic. Your formula for geometric is on your formula sheet. It's T n equals a times r to the n minus 1. So if you look, the very first one, under geometric, sequences and series, and we know when it's a Tn, it's a sequence formula, not a series formula. Series is sum, right? So it's Tn equals T1 r to the n minus 1. Well, that certainly looks a lot like the formula we were just using. A number times a number to an exponent minus 1. Like the very last box we were just dealing with, right? The only thing that's different than in this one than the last one is there's an r. There's a Tn. What does Tn stand for? Last term. What does T1 stand for? First term. What does n stand for? Number of terms. What does r stand for? Common ratio. It's the only thing that's different. And then down here it says it again. The common ratio can be found by taking any term except the first and dividing the term by the previous term. So you can take the first term, but you need to take the second term divided by it, right? The only one you can't use is the first because there's no term before it. So it's Tn minus the one before it. So if I go to do this one, r is going to be what divided by what? If I use this sequence. 15 divided by 5. Or 45 divided by 15. These should all be equal. Or 135 divided by 45. All of them is 3. It didn't matter which 2 I picked, right? They all give me 3. So here we have to determine if the sequence is geometric. How can you tell something's geometric? It has a common ratio, right? So, if this is geometric, I should be able to go 2 divided by 1, and it should equal 4 divided by 2, which should equal 8 divided by 4. Is that true? 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. Ah, it is true. What about the next one? Is it geometric? Kind of looks like it is. 8 divided by 4, 2. 4 divided by 2, 2. 2 divided by 1, 2. 1 divided by 1, nope. So it's not geometric. You try the last one. You divide them all out, you get negative 5 for your r, so it's geometric. So example 2 says, write the first 4 terms of each geometric sequence. So this one gives you T1, which is 7, and R. So I have the first term. Boom. Now I need the next 3. How do I get them?
You multiply.
By what?
-3.
Yeah. Multiply by -3, so what are you going to get? Yep. And then we multiply by -3, so we should get positive 63. And then we multiply by negative 3, and we should get negative 189. You try B. So for this one, we're going to get negative 8 times it by a half, negative 4 times it by a half, negative 2 times it by a half, negative 1. Should be halving each time when you multiply by a half, right? Now C, that's the general term. Remember the general term? You leave out the Tn and you leave out the n, and I can get any term I want from it. That's what C is. So it's the general term. So if I want term 1, I'm going to fill 1 in for n. So I'm going to get 3 times 0.6 times 1 minus 1, which is 3 times 0.6 to the 0. What's anything to the power of 0? Nope, 1. So this is actually 3 times 1, which is 3. Try 2, 3, and 4. See if you get the right answers. Let's do term 2. Equals 3 times 0.6. The 2 minus 1. So it's 3 times 0.6 to the 1. What do you get? 1.8? Term 3 is 3 times 0.6 to the 3 minus 1, which is 3 times 0.6 squared, which is, I don't know, my brain stopped at that. 1.08? And then term 4. Sorry, what's it?
0.648.
Then we're going to flip over. Okay, this one says, determine the unknown terms in each geometric sequence. So, we need to know R in order to figure this out, correct? Let's write what we do know. We know T1 is 18. What is 6174? Tn. What else do we know? Yeah, we don't know R. We know N is 4. So, what do we do when we have knowns and we need to figure out one unknown? Yeah, so we need to actually plug it into our formula. You guys have formulas on your formula sheet, right? So we need to fill it into the Tn equals T1 times R to the m. Why am I filling it into this one? Because up here, it says it's a geometric sequence. If it said it was arithmetic, I would fill it into the other Tn formula, right? So let's fill in what we do know. We know Tn is 6,174. T1 is 18. We don't know R. And N is 4 minus 1. So we have 6,174 equals 18 times R to the 3. What's the first thing I'm going to have to get rid of? The 18, because I'm doing reverse BEDMAS. BEDMAS is brackets, exponents, multiplication, division, so I have to get rid of the multiplication first. So I'm going to divide by 18. What's 6,174 divided by 18? Pardon?
340.
Thank you. Equals R cubed. How do I get rid of a cubed? Yeah. You can use the cube root. So where is the cube root? I'm going to show you how you can do it always. So if you do this, this will work for always. If you push the one button, it only works for cube, but we're going to have other roots too, okay? So practice with me. Press the 3, because we're going to practice as if we don't have a cube root button. Press 3, Then press Math, which is below the alpha button. Number 5. Do you see how there's an X there? It's going to put the 3 in that spot. So if I wanted the 5th root, I'd go 5, Math 5. If I wanted the 100th root, I'd go 100, Math 5. The cube root of 343 is 7. So my common difference is 7. My common ratio, not difference, that was stupid. Common ratio is 7. So how do I get the numbers in between? Times by 7. 18 times 7. 126. There's not enough space. 126. And then times that by 7. 882. And how do I know I'm right? Times that by 7. And I get 6,174. So it shows I'm right. We agree? We're not going to try B first. You're going to try C. Do C right now. Then we'll come back to get 2. What's up with B?
There's no T1.
There's no T1, but what can I do?
You can make the 4 the T1.
So yes, then N would change, right? So if I take a partial piece, I can do this. This can be my T1. This can be my Tn. The catch is that N is just going to be 4 in order to find N. I was going to say in order to find R, and I write R. N is going to equal 4 in order to find R. So we're going to do 108 equals 4, R to the 4 minus 1. We don't use 5 because we're treating 4 as our T1. We get 108 equals 4, R to the 3. Divide by 4. 20, pardon? 27 equals R cubed. Cube root. And R equals 3. So I use 3 to multiply to get to the ones on the right. How do I get to the one on the left? So instead of multiplying, I divide. So I'm going to go 4 times 3 is 12. 12 times 3, 36. 36 times 3 is actually 108. Now I have to go 4, not times 3, I have to go 4 divided by 3, which is just 4 divided by 3. Because if not, you're going to go 1.33333 repeating, or you're going to round it, which is even worse. So I would just do 4 divided by 3, 4 over 3. Your homework for this, we finish up geometric sequences tomorrow and start series as well. Then we're almost done the unit. But just so you know, we're putting together we're putting together sequences in series and the first unit of quadratics, putting together as one test. Why do I do that? So you have more practice with geometric sequences in series before the test hits. Because you guys can do this, you just need more practice to see a question and know what to do, see a question and know what to do, see a question and know what to do. So while we start doing quadratics, we also have daily quizzes with sequences and series questions on them. Okay? So I'm putting 2 units together for one test. Because most people can do really well on this, they just need more practice, and they don't get the time if I give it too fast. So, it's going to be page 39. Number 3 and 8. Number 3. What the? What? 1, C, and E. Why did I say 3 and 8? Where did that even? I don't know. C and E, like not even, like 8 starts with an E. I'll go with that. I don't. Oh, scary. 3 B and D. Textbook drives me nuts sometimes.
Why